In this lecture, in this video clip, I'm gonna give two examples of optimization in machine learning, which is a classification problem. The first thing is logistic regression, which is using part of the linear model for binary classification. As you may know before, when we classify two classes, we put two labels, and the choice of those two labels are either 0 and 1 or plus and minus 1. Okay, these are typical. Okay, now let's talk about one approach, which is logistic regression. Logistic regression involves using the logistic function, or there has many names, sigmoid function. Okay, which is given by this way. A sigmoid function, it is actually a CDF of logistic distribution. It's a CDF because the value range from 0 and converge to 1. Okay. In logistic regression, it plays a role in binary classification because now your response Y, they use the label of 0 and 1. Okay. Your row of X here is a predictor. Now, I'm using the notation that follow the literature in modeling. In our optimization, X is our optimization variable. Okay, but in this slide, when we talk about application, I try to use a notation that agree with that domain of application itself. Okay. So logistic regression basically use the logistic function to define the probability mass function, because of when you have a Bernoulli variable, you define the pop of y equals 1 and then it's done, because pop of y equals 0 is 1 minus that. Okay. So it's basically according to this. Okay, this is called the log of odds. Okay, the log of odds. It can be shown that is the sigmoid inverse of pop y equals 1. Okay, and you associated this with the predictors by linear equations. This is like, in terms of modeling, it basically say that my X explain Y, right? My input explain the output, but how I define it in the way that, I have this F5 function, linear function in the predictors, and it plays a role as to define the probability of one class via the inverse of a logistic function. Okay. Now in this class, we don't need to worry about that. That's a meaning. Okay. But it basically says that in terms of estimation theory, our goal is to estimate those beta. Okay. How each predictor has an influence in explain your Y. So now in our optimization context, the optimization variable is beta. Okay. Now, why is it an optimization problem? Because in terms of estimating this model, the model parameter, which is beta, has to have some optimal sense, and that sense is maximum likelihood principle. We will pick the beta that maximize the log likelihood, and this is a log likelihood of Y, which is has a Bernoulli distribution, and there's some analysis before end up having this. Before we end up having this. Okay. Now, in terms of modeling, you have to maximize this out, the log likelihood. But now we're going to flip it into our standard setting. So we minimize the negative log likelihood. So this is our cost function. If you take a look at it, like real quick, by recognizing that this sigma itself is a sigmoid function. And sigmoid function, is it linear or non-linear? Yeah, the figure speaks for itself. Is it linear or non-linear? Non-linear. And you see that, oh, you have composite of sigma with linear in beta. Now what is my z now? Because of this summation of xi, I use the compact vector form. Okay, like 1 x1 dot 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 xn inner product with a beta 0 and beta n. Okay, so my z is just this vector. Okay, think of z as what? Z come from data. Okay. Now, when you see this as an optimization problem, again, we recognize that my variable is here. Those something else, y and z, these are data. Of course, they will be given in terms of optimization problem. Y and z are problem parameters. Have to be set it beforehand. We want to solve for beta. Pilapong, is this unconstrained or constrained problem? Unconstrained. Do you have to worry about the log? The log has implicit constraint. The domain of log is what? Non-negative. Remember that the problem is called unconstrained when it does not have explicit constraint. Like implicit constraint will be treated as the domain of the problem. But because, I mean, of course, the sigmoid function, does it ever return a negative value? No, right? So this is fine. This is fine. So this is an unconstrained. Is it convex? Now this is the part where I want you to recognize. Did you see that y log something? This part log something that looks similar. If I actually the hidden meaning of this thing is that you're gonna use the output that returned by the sigmoid as y hat. I mean, this is interpretation in terms of modeling. After you do the regression, the logistic regression, I mean, the output of your model is not a discrete value as 0 or 1, but it just gives you the probability value. And you need to threshold it. Like, if this guy is what, like 0.6, you say, oh, y hat, no, I mean that classify as class 1. Okay, so this is 1 minus I, and this is just 1 minus y hat. Does it look anything familiar? It looks similar to a cross entropy function, x log x. Okay, but it just that it replaces these with the prediction y hat. Okay. Now I want you to verify. I'm not going to do it. I'm going to verify it. You're going to verify that the gradient, which is not obvious right now because beta is a vector, and you can check the Hessian matrix. Beta is it has beta 0 to beta 1, sorry, to beta n. So beta is a vector of n plus 1. What is the size of my gradients? What is the size of my Hessian? วรชิตMy optimization variable is beta, is a vector of n plus 1. My cost objective f naught is a function of beta, right? So it's a function of Rn plus 1, but it maps to to R. It's a scalar value function, but it's a function of several variables. So my gradient is going to be Rn plus 1. My Hessian is going to be a matrix of size n plus 1 times n plus 1. Now, let's take a look closely. If we don't know yet if the cost objective is convex or not, but we can take a look at the Hessian matrix. Is the Hessian matrix always positive, semi-definite or not? It's a sum of several things, right? If each I is if each I, if like what inside each I is a positive semi-definite, then the sum is always positive semi-definite. For each I, this is a scalar. This is a scalar. Easy. The output of sigmoid, is it? Is it non-negative, right? What about ZZI transpose? ZI is a vector. What do you get? It's an outer product, right? So it's quadratic form in terms of Z. So this term guaranteed to be positive semi-definite. In conclusion, the Hessian is positive semi-definite. So your objective is convex. Logistic regression is a convex problem, unconstrained. Can we derive the closed form solution? Unfortunately, no. Closed form solution mean, I derive the gradient, I set it to 0, and now I try to write beta as some closed form expression. Yeah, try to figure out, can we do that? No. Okay. Another example, very closely related, is there are other formulations that change the label of the classes from 0 and 1 into plus and minus 1. Plus and minus 1. And it's just what? It just used the objective that is called log error cost. By recognizing that you're going to define the cost that is a function of minus log of this guy when you're in this class, okay? When you're in this class, add the cost with this expression when you're in the other class, and because of some mathematical property of the sigmoid, okay, we're going to need this a little bit, okay? And those two cases, so initially it's like your cost is this expression when y is 1 is another expression when y is minus 1. But we can play with the property of sigmoid function, and it allows you to write the log error cost into a single function, which is this. Okay. And and maybe just take a look at the end result. Okay. In that case, the log is called the classification problem with the soft max loss function. Soft max loss. Again, when you take a look at it, is the variable is here. The variable is here. Of course, unconstrained problem. All right, unconstrained problem. Even though this is log, but the argument inside is guaranteed to be positive. Okay. So unconstrained. Now, is it convex or not? I mean, do not fall into this trap that I need to check convexity all the time. Okay, like a lot of application, a lot of problem in applications are non-convex, but so many others are convex too. Okay, I give this to illustrate that this is like a real problem in machine learning and happens to be convex. In order to show that it is convex, you can directly check the Hessian. But there are other ways to apply the property of the convex function as well. And one of them is the composite of log with something convex, all right? That we didn't discuss. But I want you to recognize that the argument inside, if you take a look at the function as a function of beta, is it convex or not? Huh? Convex, right? Convex, because it's exponential function. Like we have some rule, but not the. I'm not going to talk about the detail here. If you composite of log with something else, because of log that has increasing property, and that thing else, it has convex property. We have some rules to conclude that the result is still convex. But as of now, if you really want to verify whether it is convex or not, try to derive the Hessian. Okay. Now, I will skip. Okay, I will skip. I will skip to support vector machine. Okay, in the support vector machine, the class label is 1 and minus 1. They want to find a hyperplane described by normal vector W and the translation term B that classify. One important inequality, which is part of the constraint, is that your hyperplane is a good choice if it can separate data into two classes. And what I just said can be translated into mathematical constraint as these two purples. When y is 1, which is in one class, okay, you belong into this half space. Which one? Upper or lower? Upper, okay, and this one is lower, okay. And because of the class label is 1 and minus 1, these two inequalities, when you express it as constraint, these are related by and, okay. Because y is either 1 and minus 1, you can combine it into a single inequality constraint. Please check whether this single one equivalent to this and with this. Like, oh, when yi is 1, ding. When y is minus 1, ding. Okay, got it. Now, what you see in the purple is a constraint. How many constraints do you have? What is the index I here? In the context of SVM, the index I is a sample index. Like you have data points, n, big N. So this is actually I equal 1, n. Okay. Now, what I mentioned earlier is that when you want to find a hyperplane that separates two classes, you can derive that the width of this tube is a reciprocal to the norm of the normal vector. Okay. This is one homework exercise I give to junior student as well. Okay. Like the tube of two hyperplanes is actually proportional to the inverse of norm of the normal vector. So the support vector machine problem is that if you put only the purple constraints without worrying anything, this is a feasibility problem. This is a language of optimization. Find any hyperplane, like the pink one, the green one, the blue one, right? Anyone that can separate the data set. But again, if you want to have the classifier to have some optimal sense, then you have to define what that optimal sense would be. And here, I want to enlarge the margin. I want to separate the two data with the maximum margin as I can. And as we see previously, if you maximize 1 over something non-negative, positive, you can actually minimize the denominator. Right? So that's why in the context of SVM, this is the objective. They minimize the two norm. The reason why they make the square so that it makes like a quadratic function in W. Okay. What kind of problem? Can you give me the optimization variable first? Y and X are data. Optimization variable is W and B. What is the side of W? Rn. B is scalar, right? Okay. Typically, the size of a normal vector agree with your input features. Again, this is, even though we say xi, I is a sample index. Xi itself is a vector. Has many, is a vector that have different meanings in terms of variable. Okay. Soft margin SVM. Now it just modified the meaning of the optimal sense of your SVM classifier. A lot of time data cannot be separable, which means if you solve only the feasibility problem, it returns that the problem is infeasible. I cannot find any hyperplane that completely separate. Now, soft margin SVM basically means that you allow to be misclassified point. All right. So, initially you initiate the green criterion. Okay. But then it cannot be satisfied for all I. If you force something to be greater than 1, right? But some of them cannot be satisfied. So that's why you relax it. You drop from 1 to be something lower. So Zi is a positive number. Now, Zi is your introduced variable. This again is called a select variable. And then, but you don't want like many of the index I to satisfy these constraints. So you want to minimize the number of points that are misclassified. Right? How can you reflect that in the objective? So I minimize the sum of Ci as well. And this is your second objective in the course objective. The very first meaning still be kept, that you want to enlarge the margin, but at the same time, you know that classifier will not be perfect. Okay, and so you minimize some of Zi as well. Okay, and now you put the lambda here, which is non-negative value, to put a degree, whether you wanna pay attention to the misclassified point or not. Now we're gonna end this lecture. In terms of optimization, what are the variables? W, B, and Z. What is the dimension of Z? Yes, in Rn. Now your variable will be n plus small n plus 1. Okay. Now, remember that this is a problem that you minimize over W, Z, and B. Real quick, before we end the lecture, take a look at the constraint first. What kind of inequality constraint? The first one. You have to look at this as a function of variables. What kind of functions? Affine, right? Because it looks linear in W. B is a constant term. Like the constant term is actually yi times B, right? And this is linear in Z. So this is linear inequality. Can you describe it as GU less than H? Like your U is going to be all the variable. Your U is going to be a stack of W, B, and Z. The length of your U is going to be N plus 1 plus big N. Uh-huh. The second one is, of course, obviously linear in Z. If you like combine the two sets of constraints, can you like GU less than H? Okay. Agree that we have linear inequality constraints. Now let's take at the cost objective. What kind of function in terms of W and C and B? What kind of function? First is quadratic in W. The second one is linear in Z. Now, can you represent it? So then conclusion is what kind of function in U? Like U consists of 3 variables, right? First term is quadratic in U. Second one is linear in Z, which is part of the variable. So conceptually, overall, this is quadratic in U. Can you write it as this? It is quadratic, right? Okay. Now, conceptually, you have quadratic, and then what kind of constraint? Linear inequality. What type of problem? QP. So a soft margin SVM is in QP. Homework. Write it as a QP by this notation. Okay. Oh, we're not done yet. Let me just finish one thing real quick. There are another way, like by now in the research and in the modern, applications. Now we change the objective a little bit. Okay, this is called Sparse SVM. Now we replace the meaning of like minimizing the 2 norm of W, because that's the meaning of enlarging the width of the tube. But now we use the 1 norm instead. 1 norm has a property that, what is the property, Bunyadit? What is the property of 1 norm? If we minimize the 1 norm of something, what is the characteristic of the solution? Yes. If the 1 norm of a vector is small, okay, the behavior it has the W will have a lot of zeros. A vector that has a lot of zero is called a sparse. Okay, this is not hard. Okay, this is called a hinge loss. This is the same thing. I really not have time. We do, but I mean, you already did the homework. You should see that this term is actually the same thing as what we have here. Okay. It just this is just another representation of how to minimize the misclassified points. Again, but replace the 2 norm by 1 norm. So the meaning of this is, we're trying to do the soft SVM, but we prefer a sparse normal vector W, because initially after the end, when you use the SVM, what you do is that when you have a new vector X, you do this transformation, right? And okay, what do you do after you get the trained SVM? After you get the estimated W and B, right? You compute this one and see whether it's greater than 1 or lower than -1, right? To classify. So what I mean is that you're gonna have bunch of X, right? Bunch of X, and W, if W has bunch of zero, which means the corresponding feature, the variable, has no effect on your model. This is a typical one way to obtain a simple model by using a sparse, sparse scheme, sparse optimization. Is the problem convex? Why is it convex? Is this function looks convex to you? Maybe homework. Why is this problem convex? Again, you have seen the trick before. You don't have to look at this like you don't have to look at this problem, original problem. You can transform it using epigraph form. Right? You can using the epigraph form, and you see that when you use epigraph form, this part will be linear, and then you will have what? You have linear inequalities. No? And the one norm function always convex, right? Any norm is always convex. Okay, I think we only have time for this. I think next week we continue with other topics. Actually, we have a lot of applications to talk about, but unfortunately, I mean, we should discuss about algorithm point of view in next week instead. Okay. มา